About chapter number 4, physical processes. Okay, in physical processes we have like a small tank like this, and there is we use this tank to treat organics in water, organics in soil, and there's like the flow in, the charge in, concentration in, and at the end of treatment there is the charge out, let's just say out, and concentration out. It's simply like a tank, and this tank is to clean up soil with contamination or clean up water with contamination. Okay, so now we're going to use this process to see how could we model the physical process of environmental pollutants. You'll see it's either a tank or a river, and there is like a pipeline that's coming from the Ministry of Public Work. This pipeline is emitting wastewater, and you can see it's like a river, so you could just assume there's a river flowing. So there is discharge upstream, and there is concentration upstream, and here there is pollutant. Okay, a pipeline pollutant from the Ministry of Public Work. Of course, this pipeline will have discharge and concentration. And this will mix with this to produce something called flow rate downstream and concentration downstream. So this is an example of what we're going to see in this chapter. Okay? So let's look at this. Now, once we are doing physical process, we should differentiate between steady state and unsteady state. What is steady state? If any mass balance, in any mass balance situation, once there is a sufficient amount of time has passed, conditions will approach steady state. Like, for example, if you have a physical process and this physical process took a long time, sufficient time for the process to reach what? Steady state. Which means that change of mass with time is zero. Because the meaning of this is the steady state, that the concentration of and the mass of the component within the control volume remains constant. Okay? Unsteady state, there is no sufficient time that has passed since the condition has changed. Of course, we're talking about inlet concentration, flow rate, discharge, and reaction rate constant. So here, the change of the mass in the control volume did not change. Here did not change. Here, it has no. It will be variable. It will be not equal to zero. It will be different. Okay? So this is the accumulation. So for this chapter, of course, there is a lot of models available in environmental engineering booklets, but in this one, we'll be studying reactors. And we'll see what are the available reactors for this class. So these reactors are generally controlled volumes. Reactor models, we will be talking about batch reactor. We'll be talking about continuously stirred tank reactor, CSTR, and that's a continuous reactor. Sometimes they call this CMFR, completely mixed flow reactor. And sometimes the third reactor is plug flow reactor, which is a continuous reactor. So this one is a batch reactor. That's not continuous. The only continuous is the CSTR or CMFR and the plug flow reactor. What is the meaning of continuous reactor? If you have a tank, flow in continuously and flow out continuously. Continuously, it does not stop. Okay? Same thing for the plug flow reactor. Discharge in continuously and discharge out continuously. But for the batch reactor, It's like a tank. Discharge in until the tank is full. Then they close the pipe of the inlet. They'll do mixing. They'll add oxygen if needed. At the end of the treatment, they stop mixing, they stop aeration, and then they take the water. Okay? Q out. So here it's not continuous, and that's batch reactor. Here is continuous, flow in, flow out, continuously every second. And this is CSTR or CMFR. And here flow rate is continuous, and flow out, flow rate in, flow rate out is continuous, and here is plug flow reactor. So the batch reactor, as we just mentioned, that reactants are added to the reactor, and then they will do the mixing. At the end of the tank is full, they stop this, and you can see it here, and they will start the reaction, and there's no inlet, no outlet. At the end of the reaction, they'll take the water that's being, or the products that are removed at the end of the experiment. So this is the batch reactor. So let's model batch reactor first. The change of the mass over time is equal the mass flow rate in, mass flow rate minus mass flow rate out, mass flow rate of the reaction. Okay? Now, there is no mass into the control volume while reaction. So this is going to be 0. There is no mass flow rate exiting during the reaction. So this is 0, only for batch reactor, only for batch reactor. Only the mass during the reaction, mass flow rate during the reaction. Okay, so this is the equation for the batch reactor. Now, let's continue. Now we said mass, but remember we talked about it last lecture, that the mass is equal to what? C times volume. If C, let's see, either we use this unit, or if C is milligram per liter, and volume is liter, so this times this, you'll have mass. So if you multiply concentration times volume, that is mass. So whatever we did here, this one, we'll put it back here. dm over dt is equal m dot r reaction, or the reaction rate. The mass is CV, concentration volume. So dCV over dt, and the mass during the reaction is the same thing, dCV over dt, reaction. And as we said, mass is equal concentration times volume. So the volume does not change, because the batch reactor has a certain volume, and we should just fill up the batch reactor to the certain volume that we need it to. So we take the volume out, because this is cannot be inside the d over dt. It doesn't change. So v dc over dt equal the same thing here, v dc over dt reaction. Now, we are close to this point now. So in the batch reactor, the change of the concentration over time is from the chemical reaction, because there is some reaction inside the batch reactor. It's either there is a biological reaction, bacteria that are eating the chemical, or there is another chemical that is reacting with that chemical to reduce it, or there is somehow some type of activated carbon that's absorbing the chemical inside the water. So now we have to use the same equation here. Now we want to find out dC over dt for reaction. So for zero order reaction, the dC over dt for reaction is minus K. It's zero order, okay? Because remember here, it should be C, but to the power 0. And of course, it's negative. the organic or the chemical is being consumed or reduced. You integrate this, you will get this equation. So this equation is for zero order reaction for batch reactor. You cannot apply this for CSTR. For first order reaction, dC over dt minus K C, and this is first order. And this is the equation. And of course, it's a negative accumulation. So if you have a CSTR, again, in the book, the abbreviation CMFR gonna come through. But mostly in literature and in other papers, it's CSTR. It's continuously stirred tank reactor or completely mixed flow reactor. They all mean the same thing. So QNCN coming into the tank with the discharge flow and concentration N. Let's say this concentration has to be high. To the CSTR, there is mixing, and of course, if you are talking about bacteria, you have to have oxygen for this bacteria to breathe the oxygen to biologically degrade the organic. At the end of the reaction, the charge and concentration, and then you could use the flow for some other usages. Again, we were applying it the same way, the loading, mass loading, Qn times Cn to find out the mass loading. Of course, the same thing, mass loading in and mass loading out, so to see how much mass has been gone from the system. Okay, we're going to be assuming that this is completely mixed or well mixed. The concentration of a compound is the same everywhere except at the inlet. The concentration of the compound for the CSTR is the same. Even here, it's the same. Except here, it's not the same. Here it's high, and we are expecting this high concentration, once it's come to the CMFR, to be reduced to the minimum instantaneously, right away. So the concentration of the organic, of the chemical here and here is the same. Also, concentration in the reactor is the same as the outlet. So the concentration of the reactor is the same as the outlet, and it's all the same with the outlet and the end. But here it's not the same. Let's look at the CSTR modeling. We're gonna apply the big equation. The mass rate, change of the mass rate equal mass rate in minus mass rate out minus mass rate of the reaction. So we'll follow up the same equation, QNCN minus Q out. Let's just put here out to make it different. Minus Q out C out plus any changes that happened during the reaction. Okay, so now you should do it like this. Of course, this has to be C out. Volume we are assuming is constant. And C out, let's just take it C out as C, or you could make it C naught. It's up to you. So we have this equation. Now we're going to see zero order and first order. Okay. For zero order, dC over dt reaction is minus K. So here we have to put minus K. What is for first order reaction? It's minus Kc. So this is minus Kc for first order reaction. And this is for zero order. So you choose which one you're going to use. If the chemical follow a zero order, you should put minus K here. If it's first order, you should put minus Kc here. And this C is out. This out, okay? Not in, out. So if it is unsteady, VdC over dt is equal to this. This is for unsteady state. And you have to do the equation as is. For steady state, we will know that there is no change of concentration with time. So this is zero. So for steady state, the equation would be equal to 0 because steady state. There's no change of concentration with time. Now let's look at the plug flow reactor. And this is going to be the end of the slides. We'll try to finish this and then we'll do another video later on. The plug flow reactor is used to model the chemical transformation of a compound as they are transported in a system resembling a pipe. So if you have like a pipe, if you have like a duct, if you have like something, it's not like a tank like the one before. And the fluid here is moving along the pipe. Okay, so this is the initial, we call it a plug. This is the later location of the plug. The fluid is being mixed in the radial direction. Radial, see the radial? The radial direction. But not in the axial direction. It's in the radial. So radial direction mixing and no axial direction, that is a plug flow reactor. Of course, we have to do a mass balance here, the mass flow rate in and mass flow rate out. Okay, so we'll do the same model and we'll do the control model. Here you can see that there is a single fluid plug as it moves along the length of the pipe. Look at this, a single, because the things change in the radial form. So there is no axial mixing. Okay, sure there is Q in and Q out continuously, but there's no axial mixing. So mass flow rate in and mass flow rate out is 0, both. So dm change of mass flow rate is equal mass flow rate of the reaction. So now we'll follow dCV over dt equal dCV over dt for the reaction, and then you take the volume up because the volume is constant, volume here out, so volume with volume, so you'll end up with an equation similar to the batch reactor. So the plug flow reactor, for a first order reaction, it's dC over dt minus kc, and of course, if you want to do for a zero order reactor, it's dC over dt minus k, and if this is like this, you're going to follow up the same equation for the zero order reaction. Okay, so you could call this C out, and this is C in, and this is the charge in, and this is the charge out, and you can see the charge in and out is the same. Okay, for a plug flow reactor, there is some important parameter that we measure. It's the time spent in the plug flow reactor. How much time the water stayed inside the plug flow reactor? Of course, by the plug, because it's a plug moving from an initial location to a final location. The time spent is by dividing volume over the charge. Remember, volume is meter cube. The charge, meter cube per day. Meter cube with meter cube, and you'll end up with day. So volume over Q is time. And you could use it for the equation we just did before. The time here, it is volume over Q. And we call this time residence time. So this could be like this. C out equal C in E minus K volume over Q. Okay? And this is for first order. And of course, this volume, you could see it is the area of this pipe times the length. The area of the pipe times the length. And that is the total volume of we're going to be used here. The charge, of course, the charge in and out is the same. Okay. Before we end up this video, let's look at this table 4.2, which is a comparison between CMFR and plug flow reactor. Performance. Which one is the best to treat water with pollutants? Which one is the best? So, CMFR, which is the same as CSTR, and black flow reactor it's like a pipe. Here you need to find out what is the concentration out. He gave you the volume, he gave you the flow rate, and he gave you K. Let's apply the equation for the CMFR. Well, of course, he did did it right away. Remember from the equation of the black flow reactor, C out is equal Cn E minus K volume over Q. So you have Cn. You don't have Cn. Okay, so you have K, you have volume, and you have Q. So let's find C out over Cn is 0.37. And now let's look for the CMFR. If you look at the equation CMFR, this V dC over dt is equal Q C N minus Q out C out, okay, minus, let's take it as first order, minus volume K C out. This is 0. So if you want to find out how do they find this, so let's take the C out, Qn Cn is equal, okay, you take the C out as a common factor, okay, and now C out we want to do it C out over Cn. So C out over Cn, so if you do this and you move this here, it will be Qn over Q out plus volume Q. And for a CSTR, it's a continuous flow in, continuous flow out. So Qi and Q out is similar. But that's not it. Let's continue, find it like this. Okay, so if you divide this by Q, it's 1 over 1 plus volume over Q K. So you can see it's C out over Cn is here. Okay, so it's 1 over 1 plus K volume over Q. So this way of doing it is the same as you have the big full equation being derived as this. Okay, look at this. C out over Cn is equal to 0.5. So which one of these reactor performed well? Let's assume that Cn is 100 milligram per liter. Okay, what is C out for a black flow reactor? Okay, it's 37. What is C out for a CSTR? It's 50. So which one of these models, reactor models, did perform well? Of course, the black flow reactor gave you a very low concentration of organic or chemical. Okay, because this 100 went to 37. That's very good removal. While at the same condition, look at this, they both had the same condition. Volume, fixed Q, and fixed K. So the black flow reactor performed exceptionally well, or better than the CMFR or the CSTR. Now, let's look at one problem of the plug flow reactor. Let's say that we want to determine the volume needed to get C out over Cn 0.5, which means that we want to reduce the concentration of the organic to 50%. Q is known. K is known. Now let's apply the same equation to find out the volume. If you apply the volume, take this volume out, it will be like this. Rearrange the equation. Volume here is 100 liter. And of course, if you do the same thing here, rearrange the equation, you will have an equation like this. Volume here is 69 liter. Now what is the disadvantage here? You can see that in the CMFR, we could treat huge volume of wastewater or water with pollutants. While in the plug flow reactor, it will treat, but not that much, 69 liters. So CMFR could treat bigger volumes, especially if you are dealing with a lot of waste coming in to the plant. You should do a CMFR. If you have a little bit of volume coming into the plant, then you should do a plug flow reactor, because plug flow reactor could do very nice treatment. Okay? So we will stop at this point and we will finish this question in the next video.